is Sach Jaisinghe. So I'm the Chief Executive of Queensland Cyber Infrastructure Foundation, or QCIF for short. And it's my absolute pleasure this afternoon to present to you these quantum futures, talk about the opportunities of quantum and quantum computing, but also quantum and advanced technologies in general. So hopefully we have three great speakers, and hoping to go through these opportunities with you all. And certainly we may have the chance of some questions, but if not, certainly we'll open the door for follow-ups. Next slide, please, Danny. I'd like to first of all start off by acknowledging the traditional owners on the lands in which I'm speaking to you from today. And so I'm on the Turrbal and Yagara people land. I acknowledge the traditional owners of the lands from whichever part of the country you're from. I acknowledge their continuing connection to their culture and pay my respects to their elders, past, present, and emerging. Thank you. Next slide, please. Just as a FYI, this webinar is being recorded because we're hoping to share this more broadly as well. If you have any, if you don't want to be identified, or if you have any concerns, please let us know through the chat privately if you have any concerns. So just really quickly, a little bit about QCIF. So we're a not-for-profit organization here based in Queensland. The organization in various guises have been around for about more than 20 years. Our role is really about catalyzing a lot of cross-state and national activities in the domain of what we call data science and digital capabilities. We have a reasonably sized team of about 40 FTE and a total team of about 60, which includes a lot of training casuals as well. And we're all about kind of just-in-time access to these, as we all know, in-demand capabilities. We also have a few products that are kind of enterprise level. For example, we have a research data management system that's used by about 14 organizations in the country and in New Zealand as well. In terms of the research community, we're all about participating in research projects that involve data science and software solutions. And we also, of course, in order to enable that, have access to a lot of advanced computing, and obviously looking to dabble in that quantum computing as well. And all of this is kind of wrapped around quite a large program, which includes thousands of researchers and especially higher degree research students in terms of skills and training. Often I talk about QCIF being a cog. We're a cog in a very complex ecosystem around in the national landscape, and that kind of the figure there on this slide is trying to indicate the various ways that we participate in both the state and national system, and the different activities we're part of. Unfortunately, there's a lot of acronyms there, but certainly. To summarize, we work in both a national scale in building tools and infrastructure, as well as very much project by project. So if you're from the academic background, we participate in the usual suspects of competitive grants across NHMRC, ARC, MRFF, and so on. And also it's a privilege to work with the Queensland government on a number of different programs, including the quantum and advanced technology programs. Next slide. Now, one of the core objectives of this session, and certainly one of our key programs, is for TAFE students or vocational students. We are looking to expose through placements and internship opportunities for the TAFE student sector, and we'll talk a little bit about my guest speakers. We'll talk a little bit about why that's a key component of our, advancing the quantum opportunities a little throughout the talk. But for those of you who are interested, please use this QR code and to register your interest if you are keen on thinking about internships or placements. Next slide, please, Danny. All right, so our speakers today, it's my delight and privilege to introduce our three speakers. So Grant is from the Queensland government, and Grant leads the Quantum and Advanced Technologies program, a large program, highly strategic program for the government. And Grant's going to tell us a little bit about that program in the next couple of speak next. Moji is QCIF's own head of AI and quantum algorithms. So Moji is a graduate of Griffith University, having done his PhD with Griffith and really sort of describes himself as a quantum physicist, but he has a lot of real-world experience in quantum technologies, but also in advanced AI and machine learning. And last but not least, Dr. Jeff Pride, we're thrilled to have him take some time out to talk to us a little bit about PsyQuantum Australia and its vision about how to bring, the realities of the opportunities and realize the opportunities of quantum. And he'll talk a lot about the partnerships that are going to help us get to that kind of end goal. Long road, but highly, there's a lot of opportunities, and we look forward to hearing more about that from Jeff. All right, next slide, please. I think we are ready to go with Grant. Over to you, Grant, to tell us about the program from the Queensland government.
All right, thank you, Sach. Is my sound coming through okay? Yep, cool. All right, so I'm coming to you today from the Eco Sciences Precinct at Darton Park in Brisbane. I'd like to also acknowledge the traditional owners of the lands on which, in my case, is the Turrbal and Yagara people's lands, and pay my respects to elders past and present. So today's webinar is really to explore the nexus between quantum and jobs from a few different perspectives. So every government investment in technology development or technology-based economic development talks about, economic growth and jobs. So, the jobs of the future, high-value jobs, supply chain jobs, etc. So in the case of quantum, CSIRO has projected 16,000 jobs by 2040. But what are these jobs exactly? Is it just jobs for scientists, or is it broader based than that? And what should we be doing, in terms of government and industry and skills providers to enable a broader base of participation in quantum? Next slide, please, Danny. So when you mention quantum to people, this is often the picture that comes to mind. We've got cats that are alive and dead. Light is apparently a particle and a wave at the same time. And you've got all sorts of, inspiring, brilliant people who understand concepts that, most of the rest of us could never understand in 100 years. So the question is, though, where are the jobs in that? And a lot of people kind of have that question, I suppose. So, beyond jobs for a few scientists, where are the jobs? Next slide, please, Danny. So rather than make this a mystery story, I'm just cutting to the chase, basically, and saying we think quantum jobs will look a lot like this. So, jobs involving making stuff, designing stuff, maintaining stuff, programming, managing, selling, etc. So yes, we'll still need scientists, but there'll be, as we industrialize quantum technologies, there will be an increasing need for practical skills that are delivered more through the vet system and the undergraduate system. So the rest of this webinar is really going to try and unpack how we get from that sort of Schrodinger's cat conception of quantum to this much more sort of practical and accessible vision of quantum. And I guess I'd add my job, that's kind of my job in government, I suppose, is working out how we get from the Schrodinger's cat part to kind of this kind of thing. Next slide, please, Danny. So if you've seen the Queensland government's quantum strategy that was released year before last, I think, you'll see it's not actually called the quantum strategy, it's called the Quantum and Advanced Technology Strategy. And the reason for that is, I guess, to give explicit acknowledgement of the physical foundations of quantum technologies. So quantum is something that you can't actually hold in your hand. It is something like Newton's laws. Everyone kind of knows about Newton's laws. The entire sort of built environment that we live in is based on Newton's laws, but you can't hold Newton's laws in your hand. And quantum's a little bit like that as well. So the Quantum and Advanced Technology Strategy kind of says, well, if you want to do quantum computing, sensing, and communications, you're going to have to be good at the other stuff on this list, things like photonics and superconductors and microelectromechanical systems, or MEMS. But I guess the second advantage to that is if you're excellent at those things, it also opens up a vast array of possibilities in non-quantum products and technologies. So what we're trying to do in Queensland is kind of uplift all of this into a quantum and advanced technologies ecosystem. And the background for all of this will be increasingly the technical workforce. So without the skilled technicians, the operators, the maintainers, we will not be able to kind of build, operate, or scale industries around these technologies. So we have some companies in Queensland, some great companies that are already working in this sort of space. So in semiconductors, we've got Solana and Quest. In MEMS, we've got Wear Optimo and Vaxis. In superconductors and cryogenics, we've got Analog Quantum Circuits. And last but not least, we've got PsiQuantum, whose foundation technology is photonics. So, but at the moment, probably our biggest base of facilities and jobs in this space, is in our universities. Next slide, please, Danny. So there are a great many advanced technology facilities across our unis. So the ones on this screen, I won't run through them all, but these are all quantum and advanced technologies related, but there are also many others. And they all rely on technical skill sets for operations, maintenance, construction, etc. I know from experience from having dealt with some of these facilities in the past that they frequently have trouble attracting and retaining the skilled people they need to run the facilities. And another observation is that the vet sector is underutilized as a source of skills in this space. So what that means is we're often bringing in people from overseas to fill vacancies, and it also means our kids are missing out on, or our kids who are following kind of the vet type pathways are missing out on the opportunity to be employed in these sorts of fantastic jobs that we have in these facilities. Next slide, please, Danny. And just quickly, we're in the process of actually building more of these facilities. So under our strategy, we have a program called the Quantum and Advanced Technologies Commercialization Infrastructure Program. So we've funded 6 new facilities, well, actually 5 new ones and expansion of one existing one. So $28 million in all. And these aren't simply research facilities, they are open access product development and scale-up facilities that will use industry-grade equipment. So people employed in these facilities will be using the industry grade kind of equipment. Next slide. And I will just mention in passing, without stealing Jeff's thunder, obviously we're building, with PsiQuantum, we're building an entire quantum computing complex out near the airport. And that will draw on all sorts of skills. So just to kind of wrap up this little section of my talk. So what we're saying is there are enough opportunities now, and also in the pipeline for us to start connecting the dots to that layer of practical, technical skills in our vet sector. And that's what we're aiming to do. Next slide. So last year, the Queensland government, alongside the quantum strategy, launched an initiative called the Queensland Quantum Academy. The Quantum Academy is a virtual academy. It's coordinated by Kim Wood from our team here. And it's an umbrella over a range of initiatives that span school education, vet education, workforce, and university skilling. Next slide. So if you are interested in looking at the Academy, there's a web portal that sets out the various initiatives, the QR code there that you can scan with your phone. And the aim is to build this up over time as a resource that all Queenslanders who are interested in a career of quantum will be able to use. Next slide. So, and the reason for mentioning the Academy is this particular initiative, which is relevant to today's discussion, which is the Quantum Education and Employment Pathways Project. So this is being led by QCIF in collaboration with TAFE Queensland and also the Department of Environment, Tourism, Science and Innovation, my department. And it aims to work out how we can do the joining of dots that I mentioned earlier, how we can better engage TAFE students and TAFE qualified people in the substantial base of facilities that we already have in our universities as a precursor to creating a broader skills pipeline for quantum and advanced technologies. And that concludes my talk. Thank you very much.
Thanks very much, Grant. I think we have, Danny, can we take one question? Yeah, can probably take one question.
Yeah,
I'm
sure.
not sure how we facilitate it with this many people, but
Yeah, either that or we could hold questions over to the end.
at the end, all right, let's hold it to the end.
Yeah.
Thanks very much, Grant, to set that context and really about that policy position of the Queensland government, which is really, ultimately it's about building sovereign capabilities for Australia in this space and taking a leading role in quantum and advanced technologies. We're going to kind of sidestep a little bit and now get Moji to, without trying to explain Schrödinger's cat, go into some fundamentals of quantum technologies and what it means kind of in the real world challenges ahead. So over to you, Moji.
Thank you. Thanks, Grant and Sash. Yeah, my name is Moji, head of AI and quantum algorithm at QCIF. And in this part of the session, I will give you some introduction to what quantum technology is. And I try to keep it accessible to non-expert. And in doing so, I might have some claims that are technically a bit inaccurate, but I will try to make it both accessible and correct. Okay. Yep, sorry. Yep, in this first slide, I'm going to illustrate what a qubit is and what a quantum computer is. But before starting that, I want to mention that quantum technology is not only quantum computing. So anything that utilizes laws of quantum physics and laws of quantum physics are the ones that we apply to small things like photons and atoms. And before quantum physics, we couldn't explain why they behave in some unusual ways, and quantum physics helps us to do that. And from that, we can do a lot of things. And in the future slides, I will have some non-quantum computing examples as well. But in this first slide, we focus on what quantum computing is. So a quantum computer is made of qubits. Qubits is a bit like a normal bit in a normal computer. And in one bit in a normal computer, we can store 0 and 1. And then we can do operations like summation and other operations and change those numbers. We call it computations. Qubits are sort of similar, that they store 0 and 1, but one extra thing that they can do, they can store them both at once. You can have, for example, 20% 0 and 80% 1. And it means that both are there, but if you try to look and ask, what is your state? 20% of the time you get 0 and 80% of the time you get 1. And then this is like the idea of superposition, the second line, then you can have both of them at the same time until it's measured. When you measure, you always get 0 or 1, but when you don't look, they can exist in that hybrid state. And there is also entanglement. This is also when you have two qubits interact with each other, and then they become basically one system. And if you touch one of them instantaneously, the other one is affected. So technically, it's a very complicated interaction, but this superposition and entanglement allows quantum computers to do types of computation that is not possible or very slow. The more accurate way of saying is much slower on normal computers, but not for all computations. Some computations. I will ask about talk about some of the applications later. One other thing that I want to mention here to touch on briefly is that when you have one qubit, you can store one bit in here, but as you increase, you can have 2 to the power of number of qubits minus 1 states at the same time. If you have 100 qubits, you can have around 10 to the power of 30 different numbers at the same time. On a normal computer, if you have 100 bits, you can represent one of the numbers in between 10 to the 30 options that you have, but quantum computers can have all at the same time. So we cannot go and access all of these when we are starting computations, or when we are measuring at the end, we still get 100 numbers input and 100 numbers output, but in intermediate steps, they can use this huge dimensional space to make things parallel. That's one other reason why they can do computations that normal computers cannot do. Okay, next slide. Yep. So there are lots of different technologies, but here I only focus on 3 of them. This doesn't mean that other technologies are not good, but these are in more mature states, and we have more startups working on these ones, but there are many other promising technologies as well. Superconducting qubits is the most famous one. IBM, for example, and Rigetti are 2 companies that make these. We have a very small circuit. We need to cool it to millikelvin, which is not easy. And then we can use each of those circuits, small ones, as a quantum bit. And if there is one charge in them, we call it 1, and if there's 0 charge, we call it 0, and you can have both of them at the same time, and then we can pair them with each other to do entanglement, and that's how we do computations on superconducting qubits. The other promising platform is atom or ion qubits. So here you can see a illustration of a chip that I worked on at Griffith University. This was made by GTRI, and we did some modifications on that to speed up computations. And then you can see that atoms are hanging in the air. These are held by electromagnetic field, and then we use lasers to control 0 and 1s on these atoms, and each one of those atoms will be one of our qubits. So IonQ and Quantinuum are two startups that are working on this, and the strength of atom qubits are their noise is very low. So a 30 qubit Quantinuum quantum computer in some problems can do better than 400 qubit IBM ones, just because they have much lower errors. That's the power of ion ones, but the superconducting qubits one are better at having more qubits. And the third one, which is the technology of PsiQuantum and Xanadu, they use photons of light, particles of light. So these ones work at room temperature. They don't need millikelvin, but detectors will still need to be cooled to 4 Kelvin, which is much better than millikelvin that we need for superconducting qubits. And this technology is rapidly evolving. And I talk a little bit more about this one in the next slide. So yeah, photon-based measurement model for quantum computation. So in here, you use photons. You can do room temperature operations. Your detectors need to be around negative 269 degrees Celsius. The very good, important characteristic is that they act in telecom. They use telecom industry fabrication method, what we use for or internet, for example. And photons are very immune to interference from the environment. So both atoms and superconducting qubits, they are very sensitive to noise, and they need to be kept isolated from the environment and cold. But photons don't need that. And because we are using the conventional silicon photonic manufacturing techniques, it can be scaled very well. And Jeff is the expert in this area, and he will tell us more about this, but I wanted to touch on that. So some real-world applications. So we have sensing and imaging, optimization, molecular simulation, secure communications, and quantum machine learning. And this doesn't cover all the applications, but some of the more important ones that I have time to cover here. I have one slide for each one of those, so I move on to the next. Sensing and imaging is one of the oldest one. So for example, Cyros Lantern superconducting based detectors are being used by mining companies since 1990s. So before that, before 1990, we had like research and pilot tests of the technology, but since 1990s till now, mining companies have been using this. In one example of quantum technology that helped the industry in Australia and also globally. Other examples, Honeywell squid sensors, sort of similar technology. They're used for bioimaging and medical diagnostics, and Bosch also exploring MV centers is one of the quantum platforms for high precision magnetometry, means like for measuring magnetic field that has applications in a lot of areas. And go to the next one. Okay, so optimization, sorry, I made a mistake, and the title for this one is not correct. This one is about optimization. So one other important applications of quantum computers is in optimization. Examples for transport. We have an active project on this with QUT funded by Queensland government, and that we apply quantum computing to transport optimization, Q control. One of the biggest startups in Australia, quantum startups in Australia, is working with transport. New South Wales are same kind of problems. Xanadu is Canadian quantum computing startups that their chip, Borealis chip, can solve graph problems that has applications in many areas, including transport, but also like finance and telecommunications and others. D-Wave and Volkswagen are trialing live traffic routing, IPM, JP Morgan for portfolio optimization. One thing that I need to mention here is that most of these efforts at this point are proof of principle, and they are not to be concrete. With the size of computers and with the noise that they have, we haven't been able to show that we can do these computations better on quantum computers comparing to normal supercomputers. They can, because of limits in number of qubits that they have and the noise, we can apply them to smaller scale problems. But there is theoretical proof that if you have big enough quantum computers with low noise, we can do these computations extremely faster than normal computers. Next one, secure quantum communication. This one is another example, like sensing, that is already commercial. So you can use laws of quantum mechanics to sense bits to other side of the world, for example. Long distance still is a challenge, but we can do relatively long distances. And by you can send your secure code over the internet encoded on quantum particles like photons, and guarantee that nobody can copy and see them. So when they get to the other side, you check them and you will know if these were copied or not. And if not, then only the sender and you share the secure code, and you can communicate using that code, and then nobody else can know what is being communicated. So we have Quintessence Lab in Australia that is already selling products on this technology. Government agencies are using that. And then there are some other companies and banks worldwide that are trialing these. And the next slide. The other important application that is very active now in terms of research, and also many startups are working on this, is for molecular simulations for material and drug discovery. These are examples are, for example, you want to manufacture new drugs and you want to know how they behave, or you want to have better battery materials. Zapata Quantum Computing is working on that, and many other ones on molecular design and drug design. The thing is, these atoms in these small, we call them large molecules, but still they're very small, composed of like handful of atoms. The processes at that level are governed by quantum computing, and theoretically, quantum processes are very complicated for normal computers. They are very heavy computations, but if you run them on a quantum computers, they are the natural platform. They are the copy of the same system, you can call it. And so they do a much better job at simulating molecules comparing to normal computers, even supercomputers. So that's a big applications for quantum computers. And the last one, quantum machine learning. So a lot of companies are trying to leverage power of quantum computing for machine learning, including IBM, Rigetti, D-Wave. These are very large companies that are working on this. And for this one, this is still at the level of proof of concept demonstration stage. We cannot still do specifically very practical things that are provenly better with quantum computers compared to normal computers. In between the technologies that I mentioned, this is one of the least mature technologies, but we are very helpful with the vast computation power that quantum computers have. We could leverage that power and do better learning of data. At this point, some of the promising areas that they're showing good results is that when you have little bit of data on a process that is very complicated. So normal neural networks, they need a huge amount of data for complicated processes. But quantum machine learning methods have shown some promise in being better when the available data is scarce. Yep, so that brings me to the end of this talk. I just recap that there are many practical optimization, but this is still developing, and we have shown that these technologies work better at a smaller scale, but we still need better quantum computers. And PsiQuantum has the, I can say, arguably most ambitious goal here to scale this to millions of qubits. And we will build it here in Brisbane. So that's very exciting. So I hand over to Sash.
Thanks, Moji. I think you set up beautifully. Now, Jeff's going to tell us how PsiQuantum is going to tackle all of these and be successful in 12 months. Over to you, Jeff.
Something like that. Okay. How are we going? Can you see my screen okay? Fantastic. Well, thank you, Sash, and thank you, everyone. It's a real pleasure to be with you today to talk about PsiQuantum and useful quantum computing. So my name's Jeff Pride. I'm the Chief Technical Director for PsiQuantum in Australia. And yeah, let's dive right in. So first, a quick introduction to the company. PsiQuantum is a company that was founded out of Australian roots about 9 years ago. It's got about 500, grown to having over 500 people employed, and many of those are in California, but also in Australia, the UK, and around the world. And it's a company with a singular mission, which is to build the world's first useful quantum computer. So what is a useful quantum computer and why do we want to build that? And I thought to tell that story, we might go back and take a look at a little bit of history. So this is the first computer that was installed in Queensland in 1962. It's at the Computer Centre at the University of Queensland, and we can see here that apart from the blatant sexism in the text here, sadly, from the 60s, what this installation purpose of this computer was to allow people to calculate with the world with greater accuracy, and so build and engineer things with more efficiency. So this is the purpose of building a computer to do computation. It's to basically give us mastery of the world and technology, and therefore to harness all the benefits that we kind of flow on from after that. And so what we're really looking to do as we go to build a quantum computer is to take a transformational step in being able to realize applications that can revolutionize industry and that can add value to our state, to our nation, to our world, and to improve people's lives. And so quantum computing allows for that kind of step change to take us from problems that high performance computing and AI will never be able to address, by addressing problems whose structure just isn't suited to regular computing. And so Meiji already gave us an example of that in doing some kinds of chemistry computations in order to unlock new pharmaceutical life-saving drugs, to unlock new materials or processes for clean energy, to unlock new catalysts for the chemical and industrial industry, and so on. So as we look at chemistry and materials science, we need to solve quantum mechanical computational problems that regular supercomputers would take billions and billions of years to solve, even if they were 100 times or 1,000 times better than they are now. But quantum computers promise to solve those problems on human timescales like minutes or hours or days. And so in doing that and unlocking those industries, quantum computers promise to give us a huge amount of value that can be unlocked across our society. We're used to transformational revolutions, the industrial age, the digital age. Quantum computers will give us a new age like that. And that's the reason why PsiQuantum is ultra focused on what it means to build a useful quantum computer. So what is a useful quantum computer? Well, it's not something that looks like this in the lab, but this is part of the Brisbane history story. You can see there me in the background, the hair loss had already started. In the foreground, you can see Dr. Jeremy O'Brien, who's one of the founders and the CEO of PsiQuantum, and Professor Andrew White there as well. And we're in the lab there, just a few kilometers away from where I am in our Brisbane City office here. We're in the lab there back in 2003, building what's essentially the first transistor, the first quantum transistor for light, for photons, called a controlled NOT gate. And as a tabletop experiment, the size of your kitchen table, or probably much bigger than that, and not very scalable. It was working with 2 of those qubits that Moji talked about. But it's a Brisbane story, a Queensland story, an Australian story about how photonic computing got started. And it's part of a bigger story of many other players in Australia who fed into that as well. But that's not going to give us a useful machine. That's a scientific breakthrough, a demo. What's needed to get to a larger scale is a process like this. And this is where I kind of want to pause for a moment and say, if you're thinking what you've heard about from me today, and maybe touched on by some of the earlier speakers, all still sounds pretty quantum physicsy. This is where we sort of talk about an industrial transformation. And as we think about an industrial transformation, let's think about how things are changing and how that diversifies and broadens an industry and makes it more accessible. That's the journey I want to take us on here. So where we need to get to is we need to get to a machine with at least 1 million of those quantum bits or qubits that Moji was describing. Why is that? Because in order to do something that's commercially relevant and not just a proof of principle demonstration, that's the scale that we need to basically enable the machines to A, operate reliably, and to B, have enough processing power to be able to unlock the potential of those kinds of problems that I mentioned before. And in order to do that, we want to make things manufacturable and scalable. And so the PsiQuantum journey has been building off university work in fundamental quantum science, and then industrializing. And the way that things are industrialized leveraging, if you will, an existing process is through semiconductors. Trillions of dollars and 50 years have gone into developing the semiconductor industry, and now it's a tool that we can use. And PsiQuantum has mastered that along with its partners, as I'll explain in a minute. And we're now at a stage of a project where we're looking at infrastructure, concrete and steel beams and optical fiber, and putting together a machine, a data center sized facility that will enable us to tap into this quantum computing revolution. So in order to do that, PsiQuantum partnered with Queensland and Australia, and we intend to build the world's first useful scale, this 1 million+ qubit machine here in Brisbane on the back of that. And here's an artist's impression of what that facility will look like when it's brought up in several years' time. So as Moji already mentioned, the technology that PsiQuantum uses is photons, single particles of light in optical waveguides. Waveguides are wires for light, and what they really are tools that the telecommunications industry already uses to make switches, to route your internet signals around in optical fibers and so on. We partner with Global Foundries, which is a tier 1 fab. It's the same kind of facility that makes the chips that go into mobile phones and laptop computers and so on. And what's really important about those kind of tier 1 fabs is that they have process control and optimization and automated measurement facilities that allow us to do things with an intensely high quality and very, very quickly in a way that can really take something from a slow, laborious benchtop experiment to a manufacturable, scalable technology. Earlier in this year, we were really proud to announce the Omega chipset, which is a feature-complete chipset of all the integrated silicon photonic components that we need to go in to build a photonic quantum computer. So we may still make some performance improvements to some of those processes, but we have nailed down now the underlying technology that allows us to sort of package up and put together the different parts of the quantum computer. Everything from sources of single photons to the circuits that route them around and switch them right through to the detection of them, all the bits that you need to do quantum processing in a scalable and manufacturable way. The machine looks sort of something like this, artist's impression from start to finish, sources of single photons and other components on chip. We package them up with PCBs and heat sinks into a modular design, and then into something that looks like a quantum version of a 19-inch rack, if you will, a quantum version of a modular system, such as you might find in a data center, but in this case, a quantum supercomputer, a quantum computer. So the plan then is to be able to rack those up and install those. Some of those components need to be cold, so we put them into a system that's cooled down to cryogenic temperatures, along with some room temperature parts of the system. And then we have many copies of those kinds of modular racks to make, as I said earlier, a data center size facility, which is what will enable us to be able to get to that scale that we need. And by having a modular design, as we improve and upgrade components going forwards, we'll be able to increase the power of the machine by swapping in new hardware. So that's the plan that the company is following. So all of that sort of sounds maybe a little bit quantum physics-y still, but I mean, you can see what all the different underlying components of that there. There's things from, the fundamental quantum physics right through to semiconductor manufacturing, packaging, electronics, computing, test, cryogenics, large-scale infrastructure, and many other things like that. Here, for example, we're looking at something that looks pretty regular in a way and pretty crazy in another way. This is one of the cryostats that will keep, or a prototype of one of the cryostats that will keep some of our hardware cold at those, temperature of deep space that Moji was kind of talking about before. So the hardware is installed inside these systems, and in some ways it kind of looks pretty exotic, but in another way, really what it is is it's a large stainless steel box with some insulation and some vacuum pumps connected up to a cryogenic plant. A cryogenic plant is just a very fancy refrigeration plant that allows us to cool down to much, much colder temperatures. So in that regard, what we're doing is taking technology that the human race has already developed and mastered and used for other applications, such as, particle accelerators or other kinds of cryoplants are used in, industry such as the hydrogen industry. This is something broadly similar, and we're basically industrializing that part of the process as well. Not so much with, really highly bespoke and exotic technology, but standardizing things as much as possible, innovating where necessary and leveraging where we can. This is an example of where that cryostat is connected up. It's at the cryoplant at the Stanford Linear Accelerator in California. And the reason I show that is that as we build our facility in Brisbane, a cryoplant such as this is exactly what we intend to install and operate right here as part of our facility. So this is something that's not particularly quantum, but it's the sort of, it gives an indication of the surrounding technology which goes into this quantum and advanced technologies industry. So we partnered with the German cryo firm Linde, and we've ordered a cryoplant, the one that will be installed here in Brisbane. And so that will be part of our facility here as we go forwards. And as we build that facility, we're also engaging with the standard infrastructure and building industry as we build a data center sized facility. So Jacobs, the engineering company, Lend-Lease, the builders, are our partners in this project. So you can see it's a project that spans the exotic right through to things that are sort of much more everyday. Of course, it'll take us a number of years to bring that facility up. In the meantime, we'll be having a test and validation laboratory, which we intend to host at Griffith University, where we're able to test some of those submodules that I described there along the way. And in the short term, that might be a facility that's staffed by people with quantum physics PhDs. But as the technology kind of gets more and more towards deployment, there'll be far more sort of standardized, diverse testing and training that can go on as part of that facility. So I mentioned earlier that our team looks something like this. And out of the many technical people that we have on board, I want to tell you that only about a quarter of them are quantum physicists. The rest are people like photonics engineers, electronics engineers, software developers, scientific technicians, other kinds of operations and technical folks, as well as a wider range of other people. So if you get this idea that you need a quantum physics PhD in order to work in this industry, that's not necessarily the case. So thinking about PsiQuantum as we go on our journey forwards, we're still evolving what our workforce exactly will look like, but we can tell you that there's going to be a few kinds of jobs and pathways that will be part of what it looks like, not just for us, but for the broader industry. Of course, as we're building facilities, there'll be construction jobs in order to do that. And some of them might have some specialist components that relate to this quantum and advanced technologies industry. There'll also be continuing jobs at various different education levels, some of those requiring training prior to work, others with more on-the-job training. And we're working with partners such as the Queensland government and continuing to work with universities and now with QCIF and beyond about how we might expand what those pathways and work with our partners as they expand what those pathways towards the right kind of training is to come. So there are ways to engage with quantum computing now, often through the university sector, but there'll be more of those and more diverse ways to come in the future. So as a quick example of some of the kinds of job areas that you have, we have things like facility operations, which is a range of different technical levels, equipment technicians. The more specialized and the more mature industry comes, perhaps the less bespoke training those roles will need. Software engineers, hardware engineers, although some of these roles may still continue to require an undergraduate university education, it's unlikely that we're going to have anywhere near as many specialized quantum PhDs working in this field in the future, and we'll have a more and more diverse and more accessible range of roles. As I said, that's a work in progress, but this is what we think this is going to look like over the coming, 5 years and then on to 2040, that sort of timeline that Grant was talking about in the past. Again, just touching on some of the different components of the machine, there's everything from cryogenics, which in some ways is similar to what's used in parts of the mining industry, in other ways a bit different. We've got electronics, we've got engineering, we've got operations, and there are going to be a range of different roles within each of those technical categories. And I guess my role here today is to let you know what's coming, even if we don't know what all of those details of those things are going to look like for this maturing industry. Time's up, but in my last 60 seconds, I want to let you know that quantum computers will affect a range of different industries. So we've talked about the work that quantum computers will do in terms of doing computations that regular computing can't access. And that's going to transform and innovate across these kinds of industries, which are important to the state and the nation, and give an innovation advantage rather than necessarily needing to compete on labor costs or other things that are hard to do. It's going to give transformational advantages, unlocking new technical and semi-technical jobs across all of those kind of industries as well. So I think the future is really, really bright for quantum computing and the broader sector, and look forward to working with all the different partners to chart out what new exciting roles for different kinds of people will look like in the years to come. Thanks very much.
Thanks, Jeff. That's brilliant. Thank you very much. That was really helpful. Can we sneak in one question, Danny, or is it a burning question? I'm not sure how to make it work on Zoom. But while we're waiting, Jeff, maybe if I could just use my chair's privilege and ask one. So 1,000 qubits, what's this, like how much space does that translate into roughly, like square meterage wise?
Yeah, so a million physical qubits will look at several hundred logical qubits, and then we're talking about a site that's of order 100,000 plus square meters. That's not, of course, all covered in buildings, and it's a staged design. Obviously, we're thinking of building a quantum computer, and then we want to be able to have the capacity to upgrade that both by densification and other pathways. So if you think about a data center size facility, not talking about a giga data center, not that enormous scale, but if you think about a data center scale facility, that'll give you the sort of impression of what we're talking about.
Yeah, thanks, Jeff. I think if we could just put up that slide again, Danny, about the internship and placement opportunities. So just to reiterate, so it's for those of you, Jeff's done a really brilliant, Grant and Jeff did a really great job describing to you what the opportunities are for the vocational TAFE students. And this is not all about quantum physicists. So again, please do use that QR code if you're interested, because many of those facilities that Grant alluded to within the university sector are available for you to be placed in and have a kind of first-hand experience of quantum and these advanced technologies. So it's something for you as an opportunity that I think you should think about. I think there's a question in the chat about hold on a second. Yeah, so I think in terms of the opportunities available to people from other states, I guess the answer is no, because it's a Queensland government investment at the moment. But we're happy to talk to your state government in Victoria if they want to give similar opportunities. So there are some practical, parochial kind of investment that's happening in Queensland, but I'm certainly happy to speak to anybody in the Victorian government if they're interested. And there's a question here. I think this might be this is directed to you. I think we could probably only take that one question, Jeff. It's about PsiQuantum's cluster state. Which optical states are you creating? that's a very technical question.
Yeah, I feel like it's a technical question that's probably way beyond the scope of
Yeah,
what we're
understood.
doing today. I would just say in passing, just to be clear, and I perhaps didn't say this, PsyQuantum's not at a position at the moment, I'm sorry, where we're taking interns, except at the science level, but in the future, you know, we as things mature, as I said, then maybe that's a pathway that we can look at.
Thanks, Jeff. Look, I think we're just on time, so thank you so much for Grant, Moji, and Grant for your presentations, and I also thank all of you for participating. Certainly QSIF will put this video and host it somewhere, and follow-up questions, they can be directed towards QSIF, or you know, we can certainly help connect to the right folks. But again, I'm really interested in those people who are thinking about placements and internships within our university research infrastructure. And obviously part of QSIF's role as part of our grant that's funded is to help you find the right places for you to do those placements. Once again, thanks everyone, and have a good day. Good afternoon. Cheers.